Hello everyone, welcome to this webinar on microcontrollers, sensors, and actuators to help you design your microgravity research experiment. Over the next 30 minutes or so, we'll cover the basics on how to use this type of electronics, we'll go over some practical examples, and at the end, you'll learn how to build your own experiment. For this tutorial, we'll be designing an automatic motor-driven syringe mechanism that can be used to perform experiments in biology, biochemistry, or fluid dynamics. But before we begin, allow me to introduce myself. My name is Elias Solorzano. I am a space robotics engineer at MDA Corporation here in Toronto, Ontario. MDA has a long history in space technologies. We built the robotic manipulators on board the International Space Station, such as the Canadarm2 and Dexter, and scientific instruments for lunar and Martian exploration. This month, I'm happy to be one of your mentors for Shad Canada's spaceflight competition. So I'll be helping you address questions related to engineering, robotics, microcontrollers, and how to build your experiment in general. This competition is one of a kind, and you are part of more than 600 talented students across Canada developing scientific proposals for microgravity research. One of your experiments will get selected to fly on board this rocket, Blue Origin's New Shepard. So let's review the mission objectives and requirements of the competition. The main objective is to design and pitch a microgravity research experiment to a panel of experts and demonstrate in a meaningful and creative way how space can be used as a research platform, but more importantly, to show a value to the scientific community. The most common research topics in space are related to life or physical sciences, human health, engineering, but also arts and the implications that spaceflight can have in our society. A lot of groundbreaking research happens on board the International Space Station. Here you can see astronaut Thomas Pesquet performing an experiment on board ISS to study the behavior of liquids in weightlessness. But as you already know, we don't need to go to the space station to do this type of work. Suborbital rockets allow us to test experiments in weightlessness for a short period of time. For this competition, the rocket used to launch your payload is Blue Origin's New Shepard. Some of the rocket characteristics are listed here. It's a fully reusable rocket, it can provide about 3 minutes of microgravity, it can also accommodate up to 36 individual payloads, and the capsule will be used for human flights in the future. The flight trajectory of the rocket and its capsule is shown here. In total, the flight will last approximately 11 minutes, including a period of 3 minutes of microgravity. During this short period of time, you'll be able to perform your experiment. The rocket booster is designed to land vertically, and the capsule is designed to parachute down safely. At this point, a team from Blue Origin will recover the capsule and its contents. Your experiment needs to be compatible with Blue Origin's mini payload, shown on the right-hand side. Because of this, you've been provided with some design requirements in terms of size, power, and mass. You can find this in the competition's guidelines document. In terms of size, your experiment must fit within an envelope of 4 by 4 by 8 inches. If you are using a USB cable to power your device, make sure the power consumption of all your electronics does not exceed 5 volts at 900 milliamps. The payload mass should be kept under 1.1 pounds or 500 grams, and liquid volumes under 150 milliliters. You are allowed to use batteries as long as they are pre-approved nickel metal hydride batteries, which are rechargeable. Also, keep in mind that you cannot have liquids if you use batteries. You can only have either or. So immediately you realize you cannot have a powerful computer to control your experiment on board, and that's why for experiments that require multiple sensors or controlling moving parts, a small microcontroller such as an Arduino is a good option. Here's an example of a microgravity experiment I designed and flew during a parabolic flight in 2017. I used an Arduino microcontroller board to collect measurements of the pilot's control inputs and use these measurements to calculate small trajectory adjustments to achieve near-perfect zero-gravity conditions. In general, Arduino boards are suitable for low-cost and low-power microgravity experiments, just like yours, which gets us now to the main subject of this webinar. Here's a list of things we'll talk about next. First, you'll learn what a microcontroller is capable of and the type of sensors and actuators that you can interface with. We'll go over the basic coding structure in Arduino and learn about conditional statements, which are necessary to write the program. We'll also look at some basic programming examples using actual parts, like temperature sensors and LED lights. And at the end, I'll show you a tutorial on how to build a motor-driven syringe mechanism, which several teams using liquids might find useful. Alright, so what is a microcontroller? Well, it's really just a small computer which has its own CPU, memory, and input-output interfaces, all in one single chip. It allows you to interface with external devices and takes instructions in the form of a programming language. Some of the things you can do with a microcontroller are storing a program, analyzing and monitoring data from sensors, sending commands to other devices, and actuating physical parts. The focus of this webinar is on Arduino microcontrollers because they're very accessible and beginner-friendly. An Arduino is essentially a single-board microcontroller designed to create control systems and interactive projects. It is fully open source, meaning that the design of the board is accessible to the public and anyone can customize it or replicate it. It is capable of receiving and sending digital or analog data, which we'll talk about later. Also, all you need to program your Arduino is a laptop with a USB port, and you can use portable batteries to power the device on. Arduino boards come in different sizes, and that enables a wide range of engineering applications. For beginners, I recommend getting either the Arduino Uno or Arduino Mega. The Nano and Pro Mini versions are much smaller, but some soldering experience may be required to interface with older devices. Here's a basic schematic of the Arduino Uno with the main components labeled. As I mentioned before, the Arduino board can be powered using a USB port or using a battery pack. The Arduino board can also be used as a power supply for other components. As you can see at the bottom inside a red square, it has a 5V and a 3.3V power output. It can read or write analog and digital signals. As you can see, it has 6 analog pins labeled A0 to A5 inside the yellow box. Similarly, it has multiple digital pins labeled 2 to 13 shown inside the green box. Inside the blue box, you can see pins 1 and 0 corresponding to the serial communication port. The serial port is used to transfer data bytes with only 2 wires. Now, it's important that you understand the difference between analog and digital signals because sensors can output measurements in either form. An analog signal is a continuous signal that represents a measurement of the physical world. It can take any value between the minimum and maximum limits. An example of this is a sinusoidal wave. Let's say, for instance, that you are using a 5V sensor. The signal output by this sensor can be 0.01V or 4.99V or anything in between. So the values contained in an analog signal are infinitesimal. A digital signal, on the other hand, is a discrete signal in binary form. That means it uses zeros and ones to represent information. An example of this will be a square wave. Now, let's talk about the type of sensors you can use with microcontrollers like Arduino. First of all, a sensor is a device that measures a physical quantity to a certain level of accuracy of the real value. Sensor measurements are represented as electrical signals. An example of that is a photoresistor, which is a sensor that responds to changes in light intensity. The graph here shows how the resistance in the sensor, given in units of kiloohms, varies with illuminance expressed in units of lux. And of course, sensors can output measurements as analog or digital signals, which we already talked about. The photoresistor I showed you before is an example of an analog sensor that measures light intensity. Analog sensors can also be used to measure sound, pressure, and temperature, and if you're using a microcontroller, these measurements will be represented as voltage signals. Now, some examples of digital sensors are infrared or IR sensors, digital accelerometers, which monitor acceleration changes in X, Y, and Z, which is quite useful to monitor the microgravity environment for your experiment, proximity sensors that detect the presence of nearby objects, and encoders that sense changes in rotation. So in general, sensors allow us to measure physical quantities that vary over time, but we can also control a physical object using a microcontroller like Arduino. And that's why we need to talk about actuators. Actuators are devices capable of moving or controlling a mechanism or system. This allows you to change the position or velocity of an object. For this reason, there are many applications such as controlling robotic arms and grippers, crawlers, drones, opening or closing valves, etc. Actuators can be activated using a command signal from a microcontroller, provided that it has sufficient power to drive the motors. There are different types of actuators. Typically, they can be either electrical, hydraulic, or pneumatic. Examples of electric motors include DC servo motors that you can find in most multi-rotor drones nowadays, stepper motors, which we'll be using in one of our examples today, and solenoids, which are used to control linear displacement. Hydraulic actuators, such as hydraulic cylinders, use fluid that's non-compressible to transfer power to a machine. They can be found in construction machinery, hydraulic brakes, and aircraft control systems. Even inside your body, the human heart is an example of a biological hydraulic machine. Pneumatics use compressed air to generate power. Examples include vacuum generators, rotary actuators, and artificial muscles. Some examples that use pneumatic actuators are rock drills, pavement breakers, and suction grippers. Now, we can interface with these different sensors and actuators using an Arduino board, but to build a functional prototype of an automatic machine, such as your microgravity experiment, you need to understand the basics of electronic components and programming. In general, the electronic components inside a circuit can be classified into categories: passive and active components. Examples of passive components include resistors, capacitors, and inductors. And active components are things like transistors, diodes, and integrated circuits. In the next slide, I'll talk about the ones that we'll be using in the examples, but I encourage you to read more about these components on your own time. You also need a power source, which can be a DC power supply such as a battery or signal generators. In many projects, you also want to check the voltage or current flowing through your circuit. To do that, you can use a multimeter or an oscilloscope. Okay, let's talk about resistors first. Resistors are passive components with two terminals that are used to reduce current flow, adjust signal levels, divide voltage, among other applications. The amount of resistance is measured in units of ohms, which is represented by the Greek letter omega. Sometimes we express the units in kiloohms, which is the equivalent of 1000 ohms. In this webinar, we will only focus on the most common type, which is known as fixed resistor. Another basic component is the capacitor, which is a two-terminal passive component that stores electrical energy in an electric field. So you may be asking yourself, if a capacitor can store energy, how come is it different than a battery? Both of them can create electric potential, also known as voltage. The difference is in the storage medium. A capacitor stores energy in an electric field, whereas a battery stores energy in chemical form. The unit of measurement of capacitance is the farad, which is also expressed as microfarads, or the equivalent of 1/1,000,000 of a farad. In the figure on the left, you can see the symbols used to represent a capacitor in electric circuit diagrams. The last component we'll talk about is the diode, which is a semiconductor device that acts as a one-way switch for current. This allows current to flow easily in one direction and restricts it to flow in the opposite direction. A diode has a positive and negative terminal called the anode and the cathode. In general, current flows from positive to negative. A diode doesn't have specific measurement units. Instead, you measure the voltage drop across the diode. There are many types, but the one you're all familiar with is the LED, or light emitting diode, which releases energy in the form of photons when current flows through it. If you're planning to build a basic circuit for your experiment, I recommend you get a breadboard, like the one shown on the left, so you can lay out all your components without soldering them, as well as some jumper wires to make connections and a pair of cutters. So far, we've talked about the basic hardware components you'll need for your project. Now, let's go over the basics of creating a program using Arduino. The code is going to allow us to read measurements from a sensor or send commands to your actuators. One of the cool things about Arduino is that after you're done uploading the code using your PC, it will run automatically next time you power the microcontroller on, even if it's only using batteries. To write your program, you'll need to download the Arduino software, also known as Integrated Development Environment, or IDE. You'll obviously need a computer, which can be a desktop or a laptop, an Arduino board, and as I mentioned earlier in this video, I recommend starting with the Arduino Uno or Mega. Finally, you need a USB cable with a square end, so essentially a printer cable. The Arduino IDE is an application written using functions from other programming languages, such as C and C++. Some of you who end up going into engineering or computer science programs will get to learn how to use these languages. The IDE is used to write and upload programs to Arduino-compatible boards. It contains a text editor, toolbar with menus and common functions, a message area, and a virtual monitor. The user interface will look something like this when you open it. The window has an info panel at the top with different options, like creating a new file, opening recent projects, etc. There are two main buttons I've labeled here. One is called Verify, which is used to check for errors in your code. The other is called Upload, which writes the code into the Arduino. On the right-hand side, you have an option to open the serial monitor, which displays in real time the measurements from sensors or the inputs that are sent to external devices like actuators. If you click on the Tools drop-down menu, you can select the type of board and processor connected to your computer. You can also select the COM port and display the board information. Make sure you've done all of these steps before uploading your code, otherwise you'll get an error. Now let's learn how to write a code. The basic structure of an Arduino program looks like this. It basically has two main sections called the setup and loop functions, which are shown in green letters. We initialize these functions using the word void, and we use parentheses and curly brackets to specify where the code starts and where it ends. The setup function is called by the Arduino when a sketch starts. It is used to initialize variables, pin modes, or use predefined libraries. The setup function only runs once when you upload the code for the first time and after each power up or reset. The loop function allows the program to run, as the name implies, inside a loop. It runs the instructions inside the curly brackets consecutively. It does this until you disconnect the power cord or using a command called exit, which we'll talk about later. So let's have a look at a simple example called Hello World. We're not going to be using any sensors in this case, just the Arduino board connected to your computer. And we're going to be using this simple code which has the basic structure I showed you before. Notice that I've entered two lines of code in yellow. The first one, called serial.begin, sets up a parameter called baud rate, which is a measure of how many times per second a signal changes. The second line prints the message Hello World, which is going to be displayed in the serial monitor. For now, I'm going to use my camera and record my screen to show you what I'm doing. First, connect your Arduino board to your computer and open up the Arduino IDE. By default, the basic structure will appear in the text editor. Then I created a new file called hello_world. Next, go to the toolbar and select Tools. Here, you want to make sure you've selected the right board. For this example, we are using Arduino Uno. Next, click the port option to make sure you are connected to the right COM port. In this case, I'm using COM port number 5. And finally, click on Get Board Info and you should get a message that looks like this. Next, we're just going to copy and paste those two lines of code inside the setup function. Click on Verify, and if all goes well, you should see no error messages. Finally, click on Upload and just wait for a few seconds until you see the message done uploading. At this point, open up the serial monitor and you should see Hello World printed on the screen. Now, because we have the instructions to print the message inside the setup function, it only displays it once. What if we want to display Hello World consecutively every 1 second? We do that by writing the serial.println command inside the loop function as such. Here, I am also including a delay of 1000 milliseconds, which is the equivalent of 1 second. Re-upload your code and see what happens. Open up the monitor again and you should see Hello World printed every second. So that concludes our basic example. Now, to be able to generate a functional code for your experiment, you need to familiarize yourself with the data types used by Arduino. We can use this to define variables, which can be a sensor measurement that varies over time or an actuator command. The first one, called void, is a keyword used to initialize functions, and we've seen this before when we define the setup and loop functions. The next data type, called int, is used to declare integer values, which are the primary data type for number storage. We can use integers to count a number of repetitions inside a loop. Next, we have float, which is a value that has a decimal point. We'll be using this quite often in data analysis, as it requires more precision. An example of a floating point number is the average Earth gravity acceleration, which is given by 9.81 meters per second squared. Next, we have booleans, which can have only two values, true or false. So they're useful for creating conditional expressions that we'll talk about later. The char data type is used to declare characters. And at the bottom, you see other data types that I recommend you read on your own time, such as double, array, long, and short. To define a variable in a program, we use what's called statements, which are just commands that are written before the setup and loop functions. In this example, I've defined an integer variable called x, and I initialize it using a value of 2. We can manipulate this variable later on if we need to do some mathematical operations. I'll show you an example on how to do that in a moment. Here are some of the basic operators used by Arduino. Math operators allow us to execute simple arithmetic functions such as addition, subtraction, division, or calculate exponentials and percentages. Logic operators and comparison operators are typically used in conditional statements, which we'll talk about in a moment. Some of these symbols are not very intuitive, especially if this is your first time programming, so we'll do a few more examples. So let's have a look at an example that uses basic math operators. In this case, we'll write a function of the form fx equals x plus 1 with initial condition x equals 2. So what we want to do is to keep adding a value of 1 to the previous value. And here's how this simple code will look like. First, you define an integer variable called x equals 2. Next, you set up the baud rate, and we're using 9600 as in the previous examples. Inside the loop function, we write our mathematical expression. So you can tell that x is going to be updated every cycle. I've also included a delay of 1000 milliseconds, meaning that every 1 second we will display the current state of x. So I'm going to copy and paste this code into the Arduino IDE. We click on Verify, make sure there are no errors, and then click on Upload. You should now be able to visualize the changes in x in your serial monitor. Now you realize that by adding 1 to the previous value, we are just simply counting the number of repetitions inside this particular loop. The next topic we'll cover before doing more practical examples is conditional statements. The most basic one is known as the if statement, and it's used to execute actions if a certain condition or expression is true. As you can see here, if the expression in blue is true, the code executes the statements inside the green brackets. Otherwise, if the expression is false, as depicted here by the red arrow, the code skips those statements and goes directly onto the next line of code. Sometimes, if the condition is false, you still want your code to do something else inside the primary brackets. That's why we use the else if and else statements. This form of code is applicable to scenarios where you have multiple conditions and need to take actions for each of them. Another basic conditional statement is the while statement, which is similar to if, but the difference is that when the condition is true, the actions are executed inside a loop, which can only exit when the condition is false. An intuitive example is how water bottle assembly lines verify that the cap on top of the bottle is properly sealed. So you can think of this as a while loop, where the condition is whether the cap is sealed properly or not. Most of the time this condition will be true, but sometimes the camera will detect a deficiency. In other words, the condition is false, and some corrective action is needed, which can be removing the bottle using a robot. So you could easily program these steps using a while loop. So let's revisit the previous example where we had a function fx equals x plus 1 with initial condition x equals 2. This function kept adding 1 to the previous value. But let's say we want to stop the function and display the message hello world when x becomes exactly 10. To do that, we need to use a conditional statement. In this case, we'll use an if statement in combination with the logical operator equal to. As you can see here, inside the void loop, we've added that condition. So whenever x reaches exactly 10, we'll print the message hello world and stop the function using the exit command as I've shown here. Let's now copy and paste the code into the Arduino IDE and upload it to the board. And we should see the message coming up soon right after the number 10. So that's a very basic example on how to use a conditional statement. In a real-life application, this can be used as a way to monitor when a process fails and to take corrective actions. So far, we've looked at examples without hardware components, but in order to read or write values to the Arduino pins connected to an external device, we need to use these functions. The first function, pin mode, configures a specified pin as an input or an output. Digital read is used to read the value from a specified pin, and digital write is used to send a high or low value to a pin. This will make a bit more sense in the following example. In this example, we'll get to use actual hardware. We're going to write a simple program that makes a red LED light blink on and off every 2 seconds. That is, 1 second on and 1 second off. The parts I'll use for this example are the Arduino Uno, a breadboard, a red LED light, a 330 ohm resistor, and 2 jumper wires to make the power lines. The figure on the right shows how the basic circuit diagram looks like. I'll switch now to my camera, and you can see that I wired the components as it was shown in the diagram. The Arduino here is providing power to the LED, which is connected in series with the resistor. The positive terminal in the LED is connected to pin number 13 using a red wire, and the circuit loop is completed by connecting the resistor to the Arduino ground pin using a black wire. The code that makes the LED light blink periodically is quite simple. First, inside the setup function, we assign the pin mode. In this example, we'll be configuring pin 13 in the board as an output. Next, inside the loop function, we'll use the digital write function to send an alternating high or low value to pin 13. We'll be using a delay of 1000 milliseconds between high and low. So I'll copy and paste this code into the Arduino IDE and upload it to the microcontroller. And if all goes well, you should see the red light turn on and off every 2 seconds. So we'll do one more example using an external sensor. In this example, I want to take measurements from an analog temperature sensor once every half second. The parts you'll need for this are the Arduino Uno, a breadboard, the LM35 analog temperature sensor, and 3 jumper wires. Once again, I've used the circuit diagram here as a reference to connect my parts. First, the temperature sensor is placed horizontally on the board, and then we use our 3 wires to make the power, ground, and digital pin connections. In this case, the red wire goes to the 5-volt output on the Arduino, the black wire goes to the ground pin, and the yellow wire is connected to the analog A0 pin. Now let's have a look at the structure of the code. The first step is to define a variable to update our temperature measurements. In this case, I define it as an integer value called val. Next, we define a variable corresponding to the analog pin connected to our temperature sensor. Remember, we're using analog pin 0 in this case. Next, under the main setup function, we assign the baud rate. As we showed in previous examples, we are still using 9600. Now, the main instructions go inside the loop function. The first line of code inside this loop uses the analog read function, which takes measurements directly from pin A0 and stores it in our integer variable. For the next part, we use the float data type and a formula that converts the raw temperature values into engineering units. And don't worry about the specific conversion factors here. All you need to know in this example is that we are using an analog sensor, and because of that, the output is essentially a voltage signal, and we want to convert that to degrees Celsius or Fahrenheit. The conversion factor is usually specified by the manufacturer. And finally, we use the serial print command to display our results every half second, which is what we wanted. Let's do a little experiment now. I'm gonna grab the sensor with my fingers and you'll see what happens. You'll notice the temperature is increasing because I'm transferring heat by conduction to the sensor. It's now about 29, close to 30 degrees Celsius, so this example is actually useful for environmental monitoring. As a challenge for you, perhaps you can combine this with an LED light such that if the temperature exceeds a certain value, your LED light will start blinking. So you can do that as an exercise on your own time. Alright, so we've done a handful of examples with an Arduino microcontroller. We've learned how to create simple programs and how to read or write data using external devices. I think it's time now to design an experiment compatible with Blue Origin's mini payload. For this tutorial, I designed and built an automatic motor-driven syringe that can be used in biology experiments or fluid mechanics. For instance, if you want to mix fluids of different densities. I built this experiment to be compliant with the requirements of the mini payload on board the rocket. I'm going to go over the basic design methodology in the Arduino program, but I'll let you figure out some of the specifics on your own. First, let's have a look at the list of materials. For this project, I used a 5-volt stepper motor as an actuator. Specifically, I'll be using the 28 BYJ-48 stepper motor, which is a low-cost motor you can buy online, as well as the ULN 2003 driver board, which is compatible with Arduino microcontrollers. I'm going to be using the Arduino Mega, but you can use the Arduino Uno or smaller versions as well. The syringe I'll be using is a 10cc or 10 milliliter syringe. For the structural parts, I'm using 1/4 inch diameter, 5 inch long threaded rod, 2 5mm rods of the same length, a couple mounting screws to hold the motor in place, and a cylindrical coupler to connect the motor shaft to the threaded rod. You're also gonna need 6 jumper wires to make the connections. Here's a 3D model of my experiment. I created this using a CAD modeling software because I wanted to 3D print some of the parts, including the main support structure. Some of you who end up going into architecture or engineering will learn how to use these tools. I'll be making these parts open source for educators and students planning flights on board Blue Origin's New Shepard rocket. The basic components are shown labeled here. Basically, the shaft in the motor is connected to the rod using a small cylindrical coupler, which I 3D printed for this prototype. However, I strongly recommend to buy a metallic coupler to avoid misalignments. The rod is also connected to a slider, which is the 3D printed piece in the middle. The slider is supported by 2 non-threaded rods on opposite ends. A small nut is glued inside of this piece. The connection between the nut and the threaded rod effectively allows the slider and plunger in the syringe to be pulled or pushed whenever the shaft rotates. And here's one of my early tests using the complete assembly. You can clearly see how the syringe is being pulled by the slider connected to the rotating shaft. In this case, I didn't use any fluids. We can control the speed of displacement by tuning the stepper RPM. Let's now have a look at the electric diagram, which shows the motor and drive connections to the Arduino board. You can actually find this diagram and more tutorials online at makerguides.com. First, connect the motor to the driver board, and we'll use our setup jumper wires to create our data pin and power connections between the Arduino and the driver. You can see that inputs 1 to 4 in the driver are connected to digital pins 8 to 11 in the Arduino. In this wiring diagram, the power line is connected to an external power supply. However, for my demonstration, I'll connect it directly to the 5-volt output of the Arduino. But keep in mind that if you do this, the motor could actually draw too much current and it could damage your Arduino. So if you try this, do it at your own risk. The last step is generating the program, which is actually quite simple. I'm going to break down the code in 3 parts. First, we'll include a predefined library called stepper.h, which is the first line of code you see here. Next, we need to define 3 integer variables. First, we declare the number of steps per revolution. In this case, we're using the motor in full step mode, which means that a full 360-degree rotation is equivalent to 2048 steps. Then, we initialize a variable called number of revolutions, which is going to be our rotation counter. And the third variable is going to be our condition to stop the motor. In this case, I'm using a threshold of 10 revolutions. Next, we need to assign the motor step sequence. And to do that, we create a stepper object as shown at the bottom. Here, the sequence 8, 10, 9, and 11 correspond to the pins in the Arduino board. The second part of the code is the setup function, which you are already familiar with from previous examples. Here, we want to set up the speed of the motor in units of revolutions per minute, or RPM. To do that, we'll use the function myStepper.setSpeed. In this case, you notice I've selected an RPM value of 15 because that's the speed that works best for my setup based on trial and error. Next, we set up our serial baud rate to 9600, just like in our previous examples. The third and final part of the code is the loop function. In here, we want to command the actuator to rotate a number of times. We also want to monitor the number of revolutions and tell it when to stop. So, the first line of code prints the message pull syringe, because that's the motion that corresponds to a clockwise rotation in my setup. We also print the revolution counts. To command the motor to rotate, we use the function myStepper.step. This function commands the motor to step in one direction, clockwise or counterclockwise, and contains the variable we defined earlier. Remember, we assigned the value of 2048 steps per revolution. Also, notice that the sign of the variable steps per revolution is positive because I want the motor to pull the slider. If we wanted to push the slider and plunger instead, you will make this sign negative. Next, we have our counter, which has the same form of the function I showed you in example 3. And finally, we assign an if conditional statement. Here we want to stop the motor when the number of rotations is equal to 10. At this point, we'll print the message the motor has stopped and exit the loop. Now, let's do a demonstration using our code and experiment setup. In this case, I'll attempt to remove a sample of fluid from a container. The stepper motor will perform 10 full rotations before stopping, and we'll see how much fluid was removed. I'll upload the code to the Arduino board and we should see the shaft spinning. The torque provided by this motor at 15 RPM seems to be enough to retract the plunger a few millimeters, but the motion is not very smooth. Now, this project is still a work in progress and there's a lot of room for improvement. For instance, pushing the fluid back into the container didn't work well. Possible reasons for this are misalignments between components and the fact that the syringe is a little too far from the motor shaft, so perhaps I'll redesign this setup and post an update in the future. When you start building your own experiment, you'll have to do substantial ground testing to eliminate the risk of failure during suborbital flight. So that brings us to the end of this webinar. We've covered the basics of Arduino microcontrollers with some practical examples. I hope you found this useful and can grab some inspiration for your own experiment. Thanks for watching and I'll see you next time.